Example 4 on page 411. Okay, talking about exponential growth and decay. Lots of exponents and logarithms come up when you're aging things. This one talks about carbon-14 dating. Have you guys dealt with that before?
Yep.
Yeah? Okay, probably in some kind of science class. Chemistry, I'm assuming. Maybe biology.
Like the last section of chemistry.
Okay. When something dies, the theory is that the amount of radioactive carbon-14, which is an isotope of carbon, decreases as time goes on due to its half-life. Okay. Archaeologists use this fact to determine the age of a fossil based on how much carbon-14 is remaining in that fossil. Okay. The half-life of carbon-14 is 5730 years. So every 5,730 years, there's half as much carbon-14 as there was 5,730 years before that. Head smashed in Buffalo Jump in southwestern Alberta. How many of you guys have been there before? Yeah, death and destruction. Okay. I went to Dry Island Buffalo Jump. Similar thing. Is recognized as the best example of a buffalo jump in North America. The oldest bones at the site had 49.5% of the carbon-14 left than the original sample. How old were the bones when they were found? Okay. So, how do we set this up? I'm dealing with a half-life problem. Could you give me an equation that finds the half-life of something? Or that uses the half-life of something to find how much mass is remaining after so many years?
Model n equals n naught, open bracket, 1 over 2, close bracket, to the power of t over h.
Okay, good. I'm going to use m instead of n because we're talking about mass. Okay, so the mass of carbon-14 in your specimen equals the initial mass times the half-life to the power of, times 1 over 2 to the power of t over whatever the half-life of that object is. Okay, this is the half-life equation we studied last chapter. Okay, just going to change a couple things in this equation. One is that value h. I know that the half-life is 5730, so that's going to be useful. What do I do about m and m naught? I mean, I'm trying to find time, so we're going to leave that alone for now, but do we know the initial mass of the object?
No.
Do we know how much mass the object has right now?
49.5%.
Well, the only information I know about it is it's 49.5% of what it used to be.
Isn't times being
So still
multiplied
no.
by the first mass, though?
So we can't just do percentage.
You could do percentage, right? What we could do is we could just choose an arbitrary mass. If you want, you could just say the mass is 1. Or we could just leave it as m naught. Either way, we're going to end up with something like this. I'm going to replace m, the mass, the current mass, with 0.495 m naught. Why does it make sense to do that?
Percentage-wise,
Because that's all the information that I have about how much the thing weighs right now, right? It's 49.5% of its original mass. So the current mass, m, is 49.5% of what it used to be. And you could put in 5 for m naught if you wanted, or 10 for m naught if you wanted. It wouldn't matter though, because since they're on either side of the equation, I just divide them out. Right, I just divide both sides by m naught, so it disappears anyways. Okay, so you're left with 0.495 equals half to the t over 5730.
Oh my goodness.
Okay, does it make sense why I did this? Just want to make sure that's clear. Why I put 0.95 m naught in place of m?
Yes.
Yeah? Okay. Alright, what do I do now? How do I solve this? Got a variable in the exponents.
You just do log of 4.495 over log of 1.5 and then multiply that by 5.727.
Okay, log, or turn it into logarithmic form.
Yeah.
Right? So log 0.495 base 1/2 equals t over 5730. Oops. Okay? And then I guess we can multiply out that 5730. So we have 5730 times the log of 0.495 over the log of 1/2. That equals t. Okay. So somebody evaluate that for me, please.
It's 5813.08.
The what?
And it makes sense, right? 49.5% of what I started with means that just over one half-life took place. And one half-life is 5730 years. Right? And we have just a little bit more than that. You guys follow?